Damas y caballeros, tengan todos muy buenas tardes a todo nuestro público que nos está siguiendo a través de nuestras redes sociales. Hoy vamos a dar inicio a esta charla geocientífica. Tenemos como tema deslizamientos en la Cordillera Canadiense. Hoy tenemos el agrado de contar con una participación especial del doctor Brenbt. El doctor Ward es una de las principales autoridades canadienses en geología y cuaternario en ciencias del medio ambiente. Es profesor y director del Departamento de Ciencias de la Tierra en la Universidad Frase de Canadá. Cuenta con 25 años de experiencia en mapeo de superficies y terrenos, investigaciones estratigráficas y cuaternarias, interpretaciones de ingeniería y ambientales, de información geológica superficial y estudios de riesgo natural. Destacó por la colaboración de investigación local, nacional e internacional con otros geólogos, geógrafos, biólogos y físicos. Recibamos por favor así con fuertes aplausos al doctor.
I guess I would like to apologize for not speaking Spanish. I guess I should learn to speak Spanish. The next thing I'd like to say is I'd like to say how honored I am. Do you want to translate? No, you.
Yeah.
Yeah. I'd just like to say how honored I am to be here at the Geological Survey. I used to work at the Geological Survey of Canada.
Usualmente trabajo en el Servicio Geológico de Canadá.
And this is a picture, you can't see that well, of Simon Fraser University. And it is located in the area of Vancouver. And so you can see downtown Vancouver here, and this is the Pacific Ocean here, and this is salt water that extends here. I don't know if you've been to Vancouver before, but it can be very beautiful. I will try to talk slowly. I'm going to start by talking a little bit about our department. So at Simon Fraser University, we are a medium-sized university with 17 faculty, but we cover a wide range of early earth sciences. And I won't go into a lot of detail, but I'd like to highlight two people that you may be interested in collaborating with in the future. And the first is Glyn Williams-Jones, and I believe he has been interacting with people at Arequipa before. He is our physical volcanologist, and so he does a lot of work combining geophysical methods, such as you see here in terms of gravity, differential GPS, self-potential. He does some modeling as well with geochemical methods. And so he does a lot of work both in Canada, in Mount Meagher, that Gio will talk to you about in a few days, and other parts of Canada, but also in southern and central America, in terms of Chile, Ecuador, and Nicaragua. So he would be very interested in collaborating with you. Another person I think you would be interested in is Dr. Doug Stead. He is a geological engineer, and he does a lot of work in terms of landslides, both in rock and in sediment. And he does work with mining companies in terms of the stability of mine walls. He does a lot of numerical modeling as well. The department has a fair bit of equipment that could be of interest to you. I believe you already have a terrestrial laser scanner. This has been very useful for visualizing different landslides or unstable areas. And this example, it's an area in Italy, one of these famous mountain villages that are built on top of weak volcanic tuffs, and there are many landslides associated with it, and they're hoping to try and preserve some of the houses. We also do a lot of terrestrial digital photogrammetry and utilize structure for motion. We were doing this last week in the Coca Valley at both the landslides we looked at. One of the things we have recently got is a Gigapan camera that I guess speeds up the process and also reduces operator error. And getting a 3D image such as this can be really useful when you come back from the field. We also recently got a unmanned aerial vehicle, and we've mounted a camera on it, and we've utilized it to study different landslides and different other areas. This is an image of the Hope Slide, and this is a landslide I will discuss in a few minutes. It's a very large landslide, had a major effect, and people are, even though much work has been done on it, people are still collecting data. Recently, we also got a hyperspectral imaging and infrared thermography equipment, and this helps to estimate the temperatures of different slopes. This has proved very useful immediately after landslides, where we can scan the slope to see where the water was coming out, and the water is usually cooler, and it shows up on these scanned images. And another thing that Dr. Stead is very interested in is numerical modeling. And all of his students do some form of modeling, and the department has a huge array of different programs that they use to try and determine slope stability issues. And so here is the Hope Slide again, and they're modeling the initial failure. And this is another recent rock slide in Italy that they're trying to model the failure on. So that's just a little bit about the department. I will start the talk now. I encourage you to ask me questions. I have a lot of slides. The topic is very large. If I don't get through all the slides in the time allowed, that's okay. So if you have any questions, or if I use words or terminology that you're not familiar with, please ask questions. The topic I'm going to give today is, the different types of landslides that we have in the Canadian Cordillera. And so I'll talk a little bit, I'll have an introduction. I'll talk a little bit about the bedrock geology of the Canadian Cordillera. And then I'll talk a little bit about glaciation. And that's something that I think is a little bit different between Peru and the Canadian Cordillera. We had much more extensive glaciation. And that gave us a bunch of sediments that are problematic in terms of landslides. And then throughout, I'll be highlighting these differences, the aspects of the talk through case studies. And some of these studies have been done by some of my colleagues, and I will tell you about them as I'm talking. Any questions? Okay, so this is the Canadian Cordillera. So Canada is divided up into a series of provinces and territories. And the Canadian Cordillera consists of all of British Columbia, all of Yukon Territory, parts of the Northwest Territories, and parts of Alberta. As you can see from this relief map, it's a very mountainous area, and therefore we have a lot of landslides. And these landslides, as you know, affect people, different types of infrastructure, and as well as environmental aspects. And for us in the Canadian Cordillera, probably the most significant environmental aspect would be salmon. And the salmon are spawning in rivers up and down the coast, and landslides can affect water quality and affect where the fish can lay their eggs. And so trying to preserve the salmon runs is a very important aspect of much of the work that landslide experts do in Canada. So a little bit of a comparison. I don't know how many people have been to Canada, but it's big. Here we have slide I just showed you, showing the western part of Canada at approximately the same scale as this map of Peru. In Peru, you guys have around 31 million people in about 1.3 million square kilometers. And that works out to about 24 people per kilometer. Whereas in the Canadian Cordillera, we only have 4.7 million people in a little bit of a bigger area, 1.5 million kilometers squared. So we only have about 3 people per square kilometer compared to Peru. And most of that population is concentrated, about 2.5 million of them, down in the greater Vancouver area where I live. And so there are many, many remote areas of British Columbia with very few people living in. And so therefore, a lot of our landslides, in contrast to yours, where you have had very significant landslides affecting thousands of people, we have landslides that affect more infrastructure and are less likely to cause fatalities. Another difference we have between Peru and the Canadian Cordillera is where the precipitation falls. Here on your coast, it's very dry. Certainly in the Coca Valley, it was very dry. In British Columbia, it's the outer coast that is very, very wet. And so there's areas here on Vancouver Island and in the Coast Mountains that get between 5 and 8 meters of precipitation. And so therefore, we have many landslides in these areas in surficial sediments, usually associated with winter storms with very high precipitation events. In the interior, where the precipitation is largely snow, we get landslides in surficial sediments associated with the snow melt in the spring. And then we sometimes get intense storms in the summer that cause localized rainfall that can trigger landslides. So there are differences between our Cordillera and your Cordillera. I mentioned the fact that we have population concentrated in what we call the Greater Vancouver area. And as you can see from this map, it's relatively flat, and about 2.5 million people live in this area. And so they are not likely to be directly affected by landslides unless they live up in these more mountainous areas along the edge, but they are indirectly affected because landslides can affect all the transportation routes that lead to and from the Lower Mainland. And so I'll be talking about a few landslides and events that occurred here along what we call the Sea to Sky Highway, and I'll show you Porto Cove, which is located about here. I'll talk about the Hope Slide, which is located out at the end of what we call the Fraser Lowland here, and then I'll be talking about landslides in other parts of the Canadian Cordillera. Bedrock. Similar to Peru, it's extremely complex. I will try to summarize it in just a few minutes. The structure and the bedrock distribution in the Canadian Cordillera has been strongly affected by the accretion of exotic terrains that formed along a subduction zone and were abducted onto the west coast of North America. And so we can divide those up into different zones. Here on the outer coast, we have bedrock that's dominated by oceanic basalts and some island arc volcanics. When this terrain or super terrain abducted onto the coast, it formed an island arc, and now it's been eroded, and all we have is what we call the Coast Plutonic Complex. It's largely granodioritic batholiths but there's also zones of highly metamorphosed country rock associated with it. In the interior here is another large terrain that formed away from North America. It's largely dominated by metamorphic rocks that range in grade from relatively low to extremely high. And then here along what we would call the Rocky Mountains are ancestral North American sediments that formed along the passive margin. And these were deformed into a thrust and fold belt. So I'm going to start by looking at some problems we've had in terms of the rocks of the Coast Plutonic Complex. Generally, these rocks are very, very strong, but they can have adverse joint patterns. And so this is an area called Porto Cove, which is on that highway that goes up to Whistler. You may have heard that we had the Winter Olympics in 2010, and most of the events were up in Whistler. And there was concerns about this single highway. Well, about a year and a half before the Olympics started, we had a very large rockfall triggered from movement along these joints, which blocked the highway for several days. And it caused a lot of, I'm trying to think of the right word, excitement, consternation, anyway, bad feelings between the International Olympic Committee and Vancouver because of concerns about the road. So the provincial government spent $1 billion Canadian trying to fix up this road so we would not have any trouble in the Winter Olympics. I mentioned the Hope Slide before. This is a rock avalanche that formed in metamorphic rocks. It happened in 1964, before Gio's work on Mount Meager that he'll talk about next week. It was thought to be the largest historic landslide in Canada at 47 million cubic meters. It killed 4 people, and it blocked this highway for over a week. And so this was a very significant event, and that is why people are still studying the dynamics of this earthquake. We're now going to jump all the way across to the Rocky Mountains, and we're going to look at some landslides that happened in limestone rocks. This is an area called the Palliser Rock Slide. It's located not too far from Calgary, Alberta. And this was a landslide studied by Matthew Sturzenegger, who was one of Doug Stead's students. And so Matthew started studying this landslide. He actually wanted to model the failure, but he noted that there was areas that were extensively covered by vegetation and areas that were not. And he wondered if there might be 2 separate landslides. And so I suggested that he try to date the landslides with terrestrial cosmogenic nuclides. So I don't know if you guys are familiar with this dating method. It's something that I utilize quite a bit, usually to date glacial events, but it works quite well for landslides. And it's based on the fact that these surfaces here on the landslide blocks are bombarded with high energy cosmic particles, which cause atoms in the rock to split apart and form unique isotopes. And in this case, calcium in the limestone breaks down into chlorine 36. And so we can take a sample. We usually use a saw and cut a series of troughs and then chisel it out. And the rock is analyzed in an atomic mass spectrometer to count how many chlorine atoms there are. And we can, by knowing the production rate, we can then calculate an age. Does everyone understand? I don't know if my explanation is all that good. Okay. So what he found was that there were two clusterings of ages. One clustering a little below 8 and another clustering around 10. And so it seems as though there were two events. The first one occurred just, say, 1,000 years after deglaciation. And so likely undercutting of the slope by glaciers and debuttressing triggered that initial failure, and then it was followed up by a subsequent failure later. He also used this data to then model the two different events using some of the programs that Dr. Stead has in his lab. And he also published a paper on the dating in landslides, and he also did some modeling and talked about that in geomorphology. So there is some. What I'd like to talk about now, in terms of bedrock failures, is some of our younger volcanic units, mainly in tertiary in age. And this is a map that shows the distribution of tertiary aged volcanic centers throughout the Canadian Cordillera. Now, these rocks, as you know, are prone to landslides, and sometimes they can be catastrophic. And so I'm going to show you a picture from Mount Meager, which is this one. This is the Capricorn Creek landslide that happened in 2010. We had a very large collapse of this portion of Mount Meager, which triggered a debris avalanche that came down and blocked rivers. And Geo will be talking about this in more detail next week. So we're concerned about catastrophic failures from our volcanic rocks, but we're also concerned about much slower movements that happen in some of the slightly older rocks that don't represent volcanic centers anymore. This is a colleague of mine, Tim Giles. He's a geomorphologist that works for the Ministry of Forest, Lands, and Natural Resources. And the Ministry of Forest is quite often responsible for landslides that happen in forested lands throughout British Columbia. And he was a friend of mine that we both went to grad school together. And he was working on a problem around this Pineus Lake. And there's a fishing lodge located here. There is a Forest Service road that goes down the lake, and there are many summer cottages in this area. And they were having trouble with the road. There was a lot of maintenance issues with it. And they're also having issues at the fishing lodge down here in terms of doors not opening, windows not opening, floorboards buckling. And so they realized that there was some problems. Tim's initial investigations pointed to issues with the bedrock geology. And so at the surface, we have some extrusive igneous basalts that are quite rigid and fairly strong. But at depth, there is a tufaceous or igneous unit that has weathered quite a bit to clays. And so there is movement occurring in this lower unit that's being fed by water in the cracks that are opening up in the basalts. And so the movement here is basically by translation. So this is a satellite image from Google Earth showing what looks like some kind of a landslide here, and there's the fishing lodge down here, and then here's the Forest Service road. But Tim also got LiDAR run for the area. And in this case, LiDAR showed that there was not just one landslide, but there was several landslides in the area. And this was the most significant one here, but you can see there's another landslide here and another landslide here. And so the fishing lodge is located there. And if we zoom out a little bit further, we can see that this is the area I just showed you with the fishing lodge here, but there are also many other landslides around the whole drainage. It actually reminds me of the Coca Valley because everywhere we looked, we found more landslides. And so this caused a significant problem because they were not sure if this would start moving faster and fail catastrophically. So they studied it by putting in a total station survey. So they put in a series of pins on the landslide and outside the landslide, and noted that in this area above the road, they had movements of approximately 1 meter per year, and then down here around the road, movements about 50 centimeters per year. And so the implications were that they decided to actually close this fishing lodge and not let the people run it anymore, because they were concerned about the fact that so many people would be occupying this fishing lodge. They're also concerned about access to other properties in the area because of problems with the road. Okay, so any questions on the bedrock geology and some of the landslides? We have a range of landslides in different bedrock types, and I'm just giving you a brief overview. Because that is a more stable system. It's better understood than chlorine-36. There's some issues with chlorine-36 with muons and some of the water content issues. Whereas with beryllium-10, it comes from quartz, and usually you can find quartz-rich rocks. In this case, it was a limestone that didn't have any quartz. So we turn to another one of my subjects, which is glaciation. And so this is a satellite view of Canada about 20,000 years ago, where we had almost all of Canada covered by glaciers. The largest being the Laurentide ice sheet, but I'm going to talk mainly about the Cordillera ice sheet, this smaller ice sheet that just covered western Canada and parts of the United States and Alaska. And so this is the Cordillera ice sheet. Vancouver's down here, so SFU's kind of down in this area. I do a lot of work in Yukon, so I'll be heading there next week. So this had a major effect on different types of landslides that we get in the Canadian Cordillera. So I'm going to talk a little bit about the nature of some of the glacial sediments we have to deal with. And so I'm not sure exactly how familiar you guys all are with glacial sediments. This is likely what British Columbia looked like during the last glaciation. This is Greenland, and you can see that pretty well everything's covered by ice with just the mountain peaks exposed above the ice sheet. One of the main sediment types we have, we call till. And so this is something that forms from the melt out of debris in the basal part of the ice. And so here we see a beautifully striated, smooth glacial surface, and then the accumulation of this very poorly sorted material. And when that is deposited, this is what it looks like. And so, again, you guys would immediately say, well, that looks like a lahar or a debris flow. And there are many similarities between the deposits. These ones would probably have more rounded clasts in it. Also striated clasts, so clasts with scratches on them from being dragged along the surface. This deposit is usually over-consolidated because it formed under the weight of ice due to being either melted out or lodged. So it is very, very strong, and it usually does not fail or trigger a landslide. However, once it becomes weathered, this material here is much looser, it's weaker, and as well, water cannot penetrate the unweathered till, and pore water pressure can build up. And so we quite often see in British Columbia that we get debris flows forming from this weathered material sliding, hitting a gully, and then liquefying and translating into a debris flow. And I would say that debris flows are the most significant landslide hazard that we have in the Canadian Cordillera. Because of glaciation, we have lots of sediment on our slopes that can weather and then recharge these gullies to allow more debris flows to happen. And when we compare our landslide frequency in glaciated areas to unglaciated areas further to the south in Washington and Oregon in the States, we find that our landslide frequency is much higher. And the reason for that is because of glaciation providing many more sediments that can be mobilized into a debris flow. So these can affect infrastructure as well as habitation. And so this is a debris flow that triggered way up here in this gully system and then covered the Trans-Canada Highway. So this is the biggest highway in Canada. It goes from British Columbia all the way to the east coast in Newfoundland. It's our major route for transportation of goods and materials. And so when it is blocked, it has a significant effect on the economy. And so in terms of this landslide, it actually badly injured 2 people in this car and blocked the highway for several days and caused, trucks to go off the road. And so as I mentioned, these things are significant. We also have them affecting where people live. In this case, a community was built on a debris flow dominated fan that was not recognized. And debris flows came down and killed people in houses, as well as taking out bridges and causing people to drive into the void space where the bridge was and dying. So I think there was 12 to 14 people killed in the space of a month or 2. And so the response to this was to spend a lot of money and build these very large debris flow retention structures. And so this is just a view of the backside of one of them. And this is another view of a different debris flow retention structure in the same area. And these are not only expensive to build, but they're also a maintenance issue because they constantly need to be excavated out after debris flow happens. So in this case, you can see that a debris flow filled up probably about half of this basin, and then they have to come in and take out all the material and put it somewhere. I mentioned that till is usually very strong and does not fail that much, but this is an example where a deposit of very thick till actually failed and hit a community and killed 4 people. And this was a material from a final report dealing with this landslide by a bunch of colleagues that I knew when I used to work for the Ministry of Forests. And so this is an aerial view of the landslide. This is an area of very thick till, but because it was moving slowly over time, cracks developed. Water was able to infiltrate into this thick deposit and weaken it sufficiently that it lost its strength and actually failed. The debris flow actually traveled down this gully, had enough velocity that it jumped the bank and did not turn this corner, and it covered this portion of Johnson's Landing, and another portion of the landslide actually came down and went into Kootenay Lake here. So I'll just show you some pictures of what happened. This is the LiDAR again, which was able to show in great detail the location of the failure, as well as other areas of instability in the same area, able to trace out the path, map out the limit of the debris, and then show the effects of the debris flow on the fan. This is an aerial view of the source. You can see that there was intense scouring that happened down here. This is where the houses were impacted, and this is the corner that the landslide did not turn. This is a detail of the upper area again. And this is showing the effects on the houses. These all houses were either destroyed or damaged in this area. Now, interestingly enough, Gar Creek, which is this creek here, was known for debris flows. However, all the other debris flows were much smaller and did not have the velocity and momentum to actually travel up onto this surface. And these houses were thought to be safe. There was a detailed hazard evaluation and risk evaluation done, and it was thought that with all this extra material up in this area that had the potential to fail, that it was unsafe for people to return to the community, and so therefore they were forced to leave. So that was till, right? That was something that's deposited directly by a glacier. And now we're going to turn to some sediments that are deposited in front of the glacier. And so we have, in this case, we have meltwater and icebergs depositing sediments into the ocean. And so in British Columbia and Canada, we have extensive areas that have raised marine or glacial marine sediments. And because the ice sheets were so large, they actually loaded the crust and depressed it. And when the ice melted, it took time for the crust to respond. And during that time, the sea transgressed over large portions of Canada here around Hudson's Bay, here in the eastern part of Ontario and the western part of Quebec, and also all along the coast of British Columbia. And so this is what the sediments usually look like. They're relatively fine-grained, dominantly silt and clay, but they can have some coarser material in them, such as gravel and sands. Usually they were deposited by icebergs floating in the ocean. This is another example of what it looks like. This is on Baffin Island in northern Canada, and we know it's glacial marine because it has in situ shells in it. The problem with glacial marine sediments is that when the clays enter the marine environment, the salt in the water causes the clays to flocculate together, and therefore they settle out of the water column much quicker than they usually do. The problem with that is that the structure of the clays is very open, and there's a lot of water in between, and the only thing holding the clays together is the salt in the pore water of the sediment. What happens when these are lifted up out of the ocean due to isostatic rebound, then precipitation and groundwater can leach out those salts, and therefore they lose their strength and they become what we call metastable. And therefore they are very prone to landslides. And what would happen is this would collapse and then drives all the water off, and then triggers a landslide, usually by liquefaction. And so one of my colleagues that I knew when I worked in the Ministry of Forests is Martin Geertsma, and this is him attaching a motion detecting camera to evaluate this landslide that you can't quite see in the background. And this is Martin and me last year up in northeastern British Columbia looking at a large landslide in glacial lake deposits. And so he has spent a lot of his career studying marine slides. And they're very common in many of these what we call fjords along the coast of British Columbia. And probably the most famous of these is the Mink Creek slide. And so this is a fjord that's now infilled by the Skeena River. We're very concerned about these marine sediments because there are many pipelines proposed from the oil sands in Alberta through the Canadian Cordillera to the ocean here at Terrace or Kitimat, to ship oil to various parts of Asia. And the concern is that these fail on very low slopes and that the pipelines could be ruptured. If you look at air photos of the area, you see many, many scars of old quick clay slides. And you can map these out, and you can see that this area, and these are areas that have proposed pipeline routes, are full of old landslide deposits. And this is the Mink Creek slide. And for those of you who, like most of you do, study landslides, you would not even think that this very low relief, benign topography would be prone to landslides. But with these glacial marine sediments, they are very, very weak. They will liquefy, and then they will cause failure. So this is the Mink Creek landslide flowing down and then flowing down the river. You can see the relief here. Again, an aerial view of this. So you can see how mobile this material is, but also that there's some rotational aspects to the later stages of deformation. And so this is an example of these pyramid structures that typify these types of failures. And what this represents is an upper weathered crust that is usually has a certain amount of strength, and below this would be the layer that liquefied and caused failure. And this occurs at very low relief, and as it moves, this upper crust breaks up and kind of founders down into this liquefied mass. And as I mentioned also, there's some areas of rotation that occur in the head wall area. And again, very low relief, only 1.7 degrees for this to fail on. And so that's a very low angle landslide. The last glacial sediment type that I will talk about is glacial lacustrine. This is the modern environment where a glacier is close to or directly in contact with a lake, and fine-grained sediment is deposited into the lake, which then settles out of suspension. Here's an example of a fine-grained glacial lacustrine unit, and these can fail naturally where rivers undercut them and cause failure. In terms of types of movement, this is me practicing my yoga stance, but actually I'm actually standing on a rotated block of a very large landslide that Martin Geertsma and I were looking at in northeastern British Columbia. So there's certainly rotation, but there's also liquefaction and then flowing that occurs in these landslides. They can also have significant effect in terms of rivers. This is Farwell Canyon, where we have a thick sequence of glacial lacustrine sediments which has failed, and it actually blocked the river. And so in this case, this is Farwell Canyon at normal flow, and this is Farwell Canyon after it's been blocked by movement on the landslide. And the concern here is that if the lake gets big enough, it can trigger a flood that goes downstream and affects infrastructure and people. Another aspect of glaciation that has an effect on British Columbia is glacial debuttressing, and I'm sure Gio will talk about this in terms of Mount Meagher. But as the ice is retreating, and all the glaciers in British Columbia are retreating right now, we have large cracks opening up and blocks starting to get ready to topple into the valley. And here's just another view of some of these large fractures that are opening up in areas that have been recently deglaciated. So I think I'll just do one more section, and I'll talk about permafrost-related landslides. And so this is something that interests me quite a bit, and I'm curious about the comparison to Peru, because I'm sure that in Peru we have areas of permafrost, and it's simply areas that do not thaw for at least 1 year. And in Canada we have permafrost that occurs in the north where it's cold, but we also have permafrost that occurs in mountainous areas that are at high elevation. Okay, and this is Panya Lipovsky. She was this is my buddy Jeff Bond that I work with a lot in Yukon, and we were sampling these boulders for cosmogenic dating to try and date deglaciation. And this is how we sample with this big saw. And she does a lot of work on permafrost-related landslides. So she works for the Yukon Geological Survey. The problem with permafrost in soils is that you get these segregated ice lenses and bodies that form. So when the ground freezes, quite often you still have groundwater moving into the area. This can freeze in the area of permafrost and form these bands, or sometimes really thick bodies up to several meters thick, of relatively pure ice. And so if these ice-rich bodies get exposed to the air, they will melt and they will trigger landslides. And we'll talk about landslides such as this that are retrogressive thaw flow slides. And so this is just a picture showing the distribution of permafrost in Yukon where Panya works. And up in the north, it's called continuous permafrost because all the ground is frozen, all of it. And so if you dig down, sometimes only this much, sometimes maybe this much, you will hit frozen ground that you cannot dig in. As we move to the south, it becomes more discontinuous. And so areas that are frozen are ones with north-facing areas, or areas that have finer grained sediments or thicker organics, right? And then you get to the south and there's sporadic, what they call it, sporadically discontinuous, where there's not as much permafrost. This can have a significant impact on infrastructure. And so this is the Alaska Highway, which I'm going to be driving along next week. And you can see these large dips in the road that are formed by the permafrost melting underneath the road. And this can affect roads. It also affects buildings. And again, here's just another example of, it's kind of like a roller coaster ride. When you travel along the road, you can actually get airborne, when you go too fast. And this is Panya standing beside a very, very large, what we call thermokarst depression. And so in this area, there was a very thick body of segregated ice that started to melt because of disturbance due to the building of the Alaska Highway. And you can see the size of this structure that formed. So it can have significant effects on the surface morphology of the area. And it can also affect roads. So this is an area out near, in southwestern Yukon, where a large embankment is failing because of melting permafrost. And so this costs a lot of money to try and fix. It can also be associated with much larger landslides. In this case, this is a Little Salmon Lake, and a very large landslide opened up here soon after a fire. And you can see it's kind of like more like a slump type failure. But what's by far more common is what we call these retrogressive thaw flow slides. And usually what happens is the organic mat of the soil becomes disturbed either because a river undercuts it, or because of a forest fire, or possibly because of road construction. And those sediments are exposed, they lose this insulating mat of organic material, and they melt fast, they melt rapidly. And so you can see, again, similar to glacial marine sediments, these can fail on very low slopes. Okay? And here's just some other examples of very large failures that occurred in various parts of Yukon territory. There we go. And then this one here is actually the failure that I studied for my undergrad thesis a few years ago when I was working for Lionel Jackson of the Geological Survey of Canada. I know that some of you may have met Lionel. And also, the last point is that we can have permafrost in alpine areas, such as Gio's going to talk about in terms of Mount Meager. That alpine permafrost can degrade, right? You can see the beginnings of a failure developing here on Mount Steele in Yukon, and then a very large failure let go just a few weeks later that deposited a large volume of material on top of a glacier. And so this is just information on it. Traveled almost 2 kilometers down slope. It's one of our largest landslides in Western Canada. It triggered a 5.2 seismic event in terms of its contact, and some of the causative factors had to do with permafrost warming as well as glacial thinning and debuttressing in the area, and it's also an area of recent tectonics. Now, I do have more to talk about, but I think I've probably talked enough. I think it's been about 50 minutes, so I'd like to stop it there. Certainly welcome any questions you may have. If you're a little shy and don't want to ask a question in front of everybody, I'll be around for a little while. You can come up and ask me some questions after. But anyway, thank you very much, muchas gracias, for having me here. I'm really happy to be here, and I really would look forward to future collaborations with Ingemet. Thank you.
Gobierno del Perú, trabajando para todos los peruanos.